In this lecture, we will continue the conversation about the separable differential equations, and we will discuss the two most common applications of this, or rather, that lead to separable differential equations. So here's the first example. Let's read it together. And when you do a problem like this, it does help to draw a picture. So we'll maybe use a highlighter to highlight all the key ingredients. But let's see what's going on here. We have an ice cream with initial temperature of 200 Fahrenheit. So note that the question on this problem is asking us about the temperature and its relation to time. So let's introduce a function capital T of lowercase t, and let that function represent the temperature of the ice cream at time t, right? So t is, let's say, is in hours, and the capital T will then be in Fahrenheit. And using this notation, we can clearly identify 200 as what? Well, 200 seems like it's our initial temperature. And it says after 2 hours, so when T is equal to 2 hours, the temperature has decreased to 80 degrees. So that means the temperature at 2 is equal to 80. And it says the optimal temperature of eating ice cream is 25 degrees. So this is our optimal temperature, and it's asking us how many hours in the freezer. So the question is to find T such that lowercase t such that the uppercase T is equal to 25. So this is how I understand this question. And in order for us to answer this question, it would be nice to have the function T given to us. However, it is not given to us, but we can set up some sort of equation and solve for T. And the way we're going to set up the equation, the law or the principle that we're going to use here is called the Newton's law of cooling, that says that the rate of change of the temperature, so how fast the temperature changes, is proportional to the difference between the temperature and the surrounding temperature. And in this case, this is one thing I missed, is the freezer is what's cooling the ice cream, and the freezer is kept at 10 degrees. So the bigger the difference between the temperature of the ice cream and the freezer, the quicker the ice cream will be cooling off. So again, initially it was at 200 degrees. It will be rapidly cooling off, but the closer it gets to 10 degrees, the slower the rate of cooling be. So again, this is called the Newton's law of cooling, and in our case, well, we have everything we need to set up the equation, and we identified this equation as separable. And we can solve this equation by separating our variables. So let's bring the capital T to the left. Let's bring the lowercase t to the right. And let's throw the integral in there. And on the left we have ln of absolute value t minus 10. And on the right side we have kt plus c. And this is our general solution. However, we've seen this type of solutions before, so let's call this C1, and we're going to isolate the capital T. So we're going to rewrite the implicit solution explicitly. And to do that, we're going to raise exponentiate both sides. So we're going to have absolute value. So I'm going to do it quicker this time. So we're going to exponentiate. So we're going to have e to the power kt. And we can put the C1 here. But again, that C1 there can eventually, or will eventually become C2 here. And we can get rid of the absolute value and add 10 to both sides. And instead of C2, we can write C3. And here's our explicit solution. So we're going to write it explicitly like this. And to find K and C, so we have two unknown parameters here, K and C. So to find K and C, we're going to use the initial conditions. So we know that at 0, the temperature was 200. So when I replace T with 0, so if I get 10 plus C, so if I will get 200. And when I replace T with 2, I should get 80, right? So 10 plus C e to the power 2k is equal to 80. And we can use the first equation to solve for C. So C is equal to 190. And we can use that value of C and replace it into the second equation. And use our knowledge of algebra and solve this differential equation by isolating k. So e to the power 2k will be equal to 7 over 190, or 7 over 19, and 2k will be equal to ln of 7 over 19, and k will be equal to 1/2 of ln of 7 over 19. So the final answer for the temperature function will be, we'll just plug everything in. So we're going to replace C with 190. So we have 10 plus 190 e KT, but K is equal to 1/2 ln of 7 over 19, so we'll just put that in 1/2 ln 7 over 19 times T. Again, so this is our coefficient K, so you can compute it manually, but I would like to just keep it as is. And let's try to answer the question. The question was what? We have to find T, which gives us the output 25. So to answer the problem, the question in the problem, we have to solve the following equation. So T of T is equal to 25. That is, we have to set 10 plus 1 minus e to the power of 1/2 ln 7 over 15 T, and then it's equal to 25. So again, using our knowledge of algebra, to solve this exponential equation by isolating T. So we subtract 10 from both sides and then divide it by 190. Then we take a natural log of both sides. And then we find T by dividing the right hand side by this coefficient K. So we get 2 15 over 100 divided by 7 over 19. So then what is that 2.3? We used to be here. And dividing by 1/2 is the same as multiplying by 2. And finally, we use the properties of logs. And I think there's a property of logs here. So we're kind of forced to actually compute this now. So I don't know if this makes it any easier or not, but it seems like we have no choice but to compute this. So let's put it in the calculator. So the calculator tells me that the answer is 5.1. And the units here are hours. So it takes about 5.1 hours for this ice cream to cool off to the desired temperature. So this is one application of separable differential equations, and let's take a look at another one. So this type of problems are called mixing problems, and let's take a look at what's going on here. So we have a tank, and in this tank we have, as it says, 75 liters of water, and we have 3 kilograms of salt in the tank. So we have 75 liters of water, and we have 3 kilograms of salt. So I'll write that this way. So we have 3 kilograms in or per 75 liters. Okay, so we have a solution being pumped in. So the solution, here's the proportion, it's kilograms, 0.4 kilograms per liter, and at a rate of 6 liters per minute. So it comes in at 6 liters per minute. And at the same time, we have something coming out at the same rate, so 6 liters per minute. And the solution is well mixed. And the question is, find the salt concentration at time t. So, what does this tell me? The way the question is asked, it suggests me to introduce a function and let s of t be the amount of salt in the tank at time t. So t here is measured in minutes, and s will be measured in kilograms. And we are going to consider the ts dt, the units of which are the kilograms of salt per minute, and the dt will represent the dt measured in kilograms per minute will represent the rate of change of the amount of salt in the tank per time t. And we know that this rate can be computed as the incoming rate minus the outgoing rate of change of the amount of salt. So as long as we can figure out how much or how fast the salt is coming in and how fast the salt is coming out, then we'll be able to set up the equation and hopefully solve. So let's figure out how fast the salt is coming in. So to figure out how fast the salt is coming in, we have to look at this side of the picture. And the salt is coming in at 6 liters per minute, and there are 0.4 kilograms of salt per liter. So the rate at which the salt is coming in can be determined by taking 0.4, which is kilograms per liter, and multiplying it by 6 liters per minute. And that will be the rate of at which the salt is coming in. It will be exactly 2.4 kilograms per minute. Now, the rate at which the salt comes out can be found similarly. So we're going to multiply something by 6 because there are 6 liters per minute, and we just need to figure out how many kilograms of salt per liter are there. And how do we know how much salt per liter is in the tank at time t? Well, that's what S of t represents. So we take S of t and divide it by the volume of the tank, which is 75, and we multiply it by 6, and that gives us the rate at which the salt comes out. And all that together must be equal to Ts over dt. So as a result, we now have a differential equation that we can write like this one. So 2.4 minus s over, and we can probably reduce this a little bit, right? So we divide everything by 3, so 2s over 25, and maybe we can even find the common denominator here. So 25 times 2.4 is So it's 60. So 60 minus 2s over 25. And as you can tell, this is a separable differential equation. And to solve it, we're going to separate the variables. So we're going with the s on the left. So 1 over, and I think it will benefit a lot by actually factoring out the 2 here. So we're going to have 30 minus s left times 2. And when we separate it, we're going to have 30 minus s here, well, times by ds, and here we can have 2 over 25 dt, and it all makes sense now after we get all the integral signs in there. And now we integrate both sides. So here we have negative ln absolute value of 30 minus s, and one side we have 2 over 25 t plus c. We have seen this type of equations before, so this is my general solution in implicit form. To rewrite the implicit solution in explicit form, I need to isolate s in this case, so we're going to exponentiate now. So we're going to have absolute value 30 minus s, and e to the negative c1 can be my c2, and we get rid of the absolute value, introduce a new constant that represents the plus or minus c2, and then we'll solve for s. And since this is our last constant, this is what we're going to call c. So the final answer here is our s function is equal to this. So the question is now, can we find c? Because right now we have the general solution, and can we find a particular solution that satisfies the initial condition? And the question here is, do we have an initial condition? Do we know anything about how much salt was there at any given time? And the answer is yes. Initially we had 3 kilograms of salt, so S0 is equal to 3. So to find C, we're going to use the initial condition, and we're going to replace 0 for C. So S of 0 is 3. So C is equal to 27. So the particular solution that satisfies the initial condition is 30 minus 27 e to the power negative 2 over 25 t. So this is our particular solution, which we can use to find the amount of salt at any given time t. However, let's take a look at the question. The question is asking us to find the limiting amount of salt in the tank. So what exactly is the limiting amount of salt in the tank? So if we assume we let this system run forever, so the question is, will there be will the system converge to some sort of equilibrium? So will it be filled with salt, or will the salt disappear completely? And in other words, what it's asking is, as the actual word limiting suggests, it asks us to find the limit of this function as t goes to infinity. And luckily, we do know how to find any limit. So in this case, we have a very simple limit problem. As t goes to infinity, negative 2 over 25 times t goes to negative infinity, e to the negative infinity goes to 0, and the answer is, so when we multiply 0 by 27, it's still 0. 30 minus 0 is 30. So the answer is the limiting amount will be 30 kilograms. Like this, it looks that way. So yeah, we just examined two interesting applications, both of which led to the creation of a separable differential equation, which we luckily know how to solve.